Yeah, hi Ritik. I'm so sorry I couldn't answer you. I'll just make you the host and then I'll be leaving the meeting.
Okay.
Just 1 second. Huh? Yeah, Ritik, I've made you the host and I'm leaving the meeting. You can take it forward from here. Okay, cool.
Okay, cool.
Okay, thank you.
Thank you. Hey, hello. Can you guys hear me? Or am I disconnected because I am facing some internet issues?
You're audible, sir.
I am audible. Okay, cool. If there is issue with some Google, then my Gmail is not working. Very interesting. Cool. So let's wait for a few more minutes and we'll give some others to join. Start by 8:05. Cool. So welcome everybody. So uh, cool. So looks like we have a decent amount of people, and very interestingly, the number of people are quite under. Looks like 16 people. So today we'll go and discuss, continue building on top of our data structures and algorithms. And how many of you were present in last class when we were discussing hash table and hash maps? A quick thumbs up. You have option there in the reaction section. 1, 2, 3, 4. Okay, so if you guys noticed last time, we had to end it. When we ended, right? There was some real world problems with sets and maps that we couldn't go through. So I'll start from there, and then the agenda will move towards binary trees. So that's next in line. And so for people who didn't attend, I am hoping you guys are aware of hash map and hash sets, and in general hash table sort of data structures. So that's what was discussed in last class. So yeah, and a very hard deadline today. So whatever we will able to cover on binary trees, I'll continue with that. And if time permits, we'll have some basic knowledge about heaps also. So that's the agenda for today. Cool. Moving on to, let me start by sharing screen. Cool. So here we are. Cool. So this is what till we saw this, right? Example and how these things work. So a quick recap. So what is hash code and what is equals? And um, so equals and hash codes, if you would guys remember, is part of the object is the base class of Java, right? So within that we have equals and hash codes, and hash code gives you a number or a code used for making up the hash, so which is used as a feed to the algorithm which decides which place it should go. And equals defines equality, or if the object is same or not, right? So in case you are implementing, so mostly anywhere if you are using hash map uh, or a hash set, you should overwrite the hash code method for a better, with a good algorithm to reduce collision. So let's quickly read this problem, and anyone who can volunteer. I think we did this. We did this problem. This is a built up. If you guys remember, right? This is a problem we did for binary search also, right? So same problem. We'll try to optimize it once, even more. So how many of we? So anyone who can volunteer and tell the binary search, and binary, there was one more approach, Bruce. What would be the solution of this problem? Just and just go over and then speak. So someone will need to volunteer, right? Otherwise, this problem solving the best worked out to, right? So anyone who can volunteer in here? No one. Okay. So so this is a very interview question. What it is asking is, you are given with an array. Are you guys able to hear me, everyone? Or I lost you guys?
Yeah, we can hear you.
Okay, cool. So, will be some or other volunteers. So, this is a typical interview question in which you are given with an array or whatever it can be, one dimensional. You are given with another number x, and what you have to do is like find two numbers, that is a pair uh, within the where the pair sum is equal to x, right? So if you see in the example 0, 1, 2, 3, 6 is the array, and x is equal to 5, and what we see that inside the array there are two numbers, 2 comma 3 and 1 comma 4, two pairs whose sum is to 5. Correct? So very interestingly, one observation, it's not necessary that they should be adjacent to each other. The pairs can be anywhere and the array is not sorted. And in case you don't find something here, you need to print. So what would be the brute force approach of solving this problem?
One way like I could think of, yeah, like for the O n square method, that is just have outer loop and inner loop. So let's start with I, like like in the outer loop I is equal to 0 to n, then in the inner loop j is equal to I plus 1 to n. Then we'll do like and yeah, we'll do I plus j, I mean that array of I plus array of j, if it is equal to 5, then just break the loop and say true. Otherwise yeah, keep going, and once all the elements have been verified, print false. So that's O n square method. Yeah.
Right. So that's n square method, right?
Yeah.
So that's what is the brute force for this. Can someone tell me what did we discuss in the binary search? What was the time complexity and how can we do that using binary search?
Binary is O log n will be the time complexity.
Yeah, binary search is O log n. And what would be the approach of this solving using binary search?
Okay,
We'll have to find the difference, and then we can find that difference using the binary search.
Correct. Before that, what you will have to do?
So we have to sort the array first, which itself will take
n log n.
n log n.
N log n, right? So O of n log n plus binary search. If you do sort using quick sort, it will be n log n. And then O of n log n and plus you will do binary search, which will be log n, which also will be n log n. Correct? For each element, you will do a binary search. Correct? So you will take the first element, find the difference minus that AI, and do a binary search and look for the difference inside the array, right? So for each element, you are doing a binary search, so it will be n log n. So n log n, 2 n log n, big O of n 2 n log n equal to n log n, correct? So this is better than the n square approach. But now if you have to do it in n, right? Then how can you do it?
Using a map, like we can store the values, initial values as key and the difference as the value, and we can look for the value by again parsing the map.
So your initial value, correct?
Sorry, I didn't hear properly.
So you are telling your initial value would be correct. Can you hear me?
Your voice broke. I don't know. Can you repeat?
Can you repeat what will you store?
So there will be a map, and the key will be these values, the input list values 0, 1, 2, 3, 4, 5, 6, and the value in that with the key will be the difference. Like 5 minus 0 is 5, 5 minus 1 is 4. So along with 0 as key, the value will be 5. So first
Okay.
I'll do this, and then I'll again parse the map and check if the value exists in the map.
So do you think that
That would be n plus n, O of n plus O of n.
so you are saying you will have something, if this is the key and if this is the value, you will have 0 comma value would be 5 in this case, correct? 1 comma 4, correct? 2 comma 3, 3 comma 2.
We don't see your screen, I believe, if you're showing
Yeah,
something.
it's frozen.
You can also do it using the hash set.
Yeah, we can. So just okay, we'll come to that. But can you guys see my screen now?
Yeah.
We can see the slides, but if you were typing in different program, that we were not able to see.
Okay. Maybe I'm just sharing the. Can you guys see the Sublime text?
Not yet.
What, you guys are still seeing the slide?
Nothing actually.
No one is seeing anything?
It is simply saying like a started screen sharing. Nothing else is being shown.
Yeah, same for me also.
Hey everybody, can you guys hear me now clearly?
Yes, we can hear.
sorry, looks like there was some internet issue and it's back now. Cool. So let me again share. Now, do you guys see some other screen?
Yes, we can see Sublime Text.
Okay, cool. So this is what you were telling, right? You will have the keys as the values and the different, sorry, keys as the original array item and the values as the difference of it, correct?
Right.
So how would you, will this help and what will you do now?
Then I can look for like values if they exist already in the list. Like
No.
the pair 2, 3 and 3, 2. So
How will you do that? So once you have done, you have entered this thing. Now, okay, you have spent already n time, correct? You iterated and then you made this map, correct?
right.
Now what will you do?
Hmm.
We can check like whether it is value is same. For 0 it is 5 values check. Then if it is not matching, then like we can tell that it's not like that. We can check for entire thing in a loop for n times.
You will again iterate over all the keys. No, what do you mean by, so you have to tell in terms of computer, how will it work, right?
Right.
We can check, of course, from manually. If you see, you can do whatever, right? But in terms of algorithmic explanation, how will you do?
Now we will again. It will iterate for the n times. For telling like it will check for this one. The value is 5 or not. That it will check for like value for in a loop. For in a loop, it will iterate and check the value is equal to 5 or not. If it is not equal to that term, if it is equal, then it will print that numbers.
On what will you iterate? Will you iterate on array or will you iterate on the map?
Map.
How would you iterate on map? How do you iterate on map?
Key like the first one like I hash map
Okay,
value.
so key set, you get the key set and then
Yes.
iterate over it, right?
Yes.
So you get 0. Now what will you do?
Okay. For 0, for the key 0, what is the value? Whether it is equal to 5 or not, that we will check. If it is not, if it is equal, then we will print that value, or else we will not print this one.
I'm so sorry. Can you please repeat the problem statement one more time?
So the problem statement is that you have an array, and in that array there are some numbers you have, and you are given with another number called x. What you need to find two numbers in the array where sum is equal to x.
We can do one thing. Suppose we have to take, if we take two for loops in the map. So first for loop counter will start from the first position I, and then the next for loop will be j minus I. We can do like that. So we'll check that if 5, suppose the
So
counter is on 5,
yeah, that we have
and
already discussed actually. That is a brute force approach where it is n square, and then we did a binary search approach where is over n log n. What we are trying to do is build this solution using n time complexity.
So,
or
Ritvik,
use
what we'll do in this approach, the key value 1, we will parse through the map. We will look if the like for the in the first iteration we have key as 0. We'll take the value that is 5 and we'll check if there is any key which is equal to 5. So that is false, and when we come to the third key value pair, that is 2 and 3. So what will happen, key 2 has value 3 and we'll check if 3 is any key in the map, and the next key is 3, so we'll get a pair.
Cool. Yeah, that works like a, but that is a better approach. But do you think that will work? Okay, no. So now think about 1,4. Will it work?
No,
Sorry,
since
that's not a correct approach.
so 1.
1,4 is equal to 5, right? You will get key 1, you get value 4, and what you look for 4 is present in the key set or not, right? It's not present, right?
Right.
So this will not work, right?
Right.
Cool. So it's simple. What we can do is this, right? For each item, just iterate over the array, add that item, and then search the difference if it is already present in the set or not. So what will that mean? I will start with this here. I get 0 first. I add it in the array. Okay. And then what I look, 5 minus 0, which is 5, is it already present in the set? No, it is not present. Fine. Go ahead. I get 1. I add it in the array. I look for 5 minus 1, which is 4. Is it present? No, it is not present. Go ahead. Similarly, I go for 2. Is it? I add 3 is not present. Go ahead. I add 4. Look for 1. Is it present? Yes, 1 is present. So I get my first pair as 1, 4. Correct? Similarly, now when I come to 3, I add 3 and look for 5 minus 3, which is 2. Is it already present in the set? Yes, it is present. So what I will get? 2, 3. Right? And then what? I add 6 and look for minus 1. Is it present? No, it is not present. So this is how you do it. And if you see what I am doing, I am just iterating on the loop once. And for each item, I am looking the set, the other item, right? So like the binary search. But what's best, what unique about this lookup is that it happens in constant time, right? So what it is doing, my for loop is running with n, and what it is doing inside, it is searching, but it is only taking constant time, right? So n into 1, right? So which is n. So overall, my time complexity is just big O of n. All of you got this thing? Or was I clear with the set approach?
Yes.
Cool. So, yep. And in case, what if I have iterated over all of my array and I don't find any pairs, I can keep a Boolean variable for it. And what I can just simply do is towards the end that, okay, just print out -1. So that's the, let me just look if I have a code for it. Yeah, pair sum. So yeah, as simple as this, right? So you look, so find pairs is, it takes an array and it takes a sum. I have taken a hash set, right? I have kept a Boolean variable. I am iterating over the array once, taking up the difference, checking condition if s contains difference, yes, I found the pair, right? And setting found as true, and also adding up the current item in there. And when I come out of the loop, if not found, then I print no matching exists. So this is a very simple case of using hash map to, or in fact hash set here. You can use hash map also. All you care about is key. The value can be anything, doesn't matter. So that's what you can do here, because what you are worrying about is just the key here, right? So, so yeah, for 16, I'm getting 1, 6. For 100, I'm getting no pair exists. Cool. So this is an example. Now this is a very interesting and another way question. So Everyone can see this slide, right? So what it is, right? This is a use case where there is a hotel, and the hotel wants to implement an algorithm where it can find at a given at any moment how many guests are there with an anagrammed name. So what I have to implement is this method anagram name, where it will take a name and it will return me that, okay, currently there are this many people in there, right? So uh, to give an example, say there are 6 guests in a hotel now with the following names: ABC, BAC, CAB, AAB, BAA, PQR, right? And if I ask anagrammed name is equal to ABC, so what is anagram? Can someone tell me first?
Which have the same set of characters but arranged in different order.
Yeah, so anagram name ABC, we have 3. Why? Because ABC, BAC, and CAB are anagrams, right? So anagram name AAB is just 2, AAB and BAA, and PQR is just 1, right? So what do you think we can use in here, and how can we solve this problem?
So what we can do is use go through the array. For every element we sort the characters and we place it in the set and make a pair as like the value as 1. For every next element we sort the characters, check if there is already a present value in the set. If yes, then increment the value 1. If not, then add another element to the set of the
And
sorted
how would you store a value in a set?
key. As the sorted value will be the key and the value will be the count.
So you should use a map, right? So not a set.
Map.
Yeah, cool. Yeah, correct. So, and now when you have to get the implement this thing, get anagram name, what will you do? How would you implement this?
Iterate over every element, sort the string by character. Sort the string by character, as in if it's ABC, then you sort it ABC in that order. So BAC will also turn to ABC when like you sort it ascending. And the first, like every element you sort, you check if the map has the key. If it has, then the value should be incremented by 1 so that you have found a match. And at the end, your key value pairs will give you the basically the elements and how many occurrences there are.
Okay, so that's something like a data structure which you have found, right? So what I am asking is, like, so in a think of a hotel guest system, it stores everything, right? And there is a API which will, given a name, it will give you all the anagrammed count of names. So that's what we need. So in that case, you just need to sort it again and do a lookup from the map. So yeah, that will work almost. Guys, why are we sorting? Can someone tell me? So someone else apart from
sorting brings all like if you have BA and ABB, if you sort it, we'll get it into a single pair.
Correct. So sorting an anagram makes the same string, right? So that's how you can store. So in terms of implementation, if I am doing, so sorry, should be named. So what I can do is, like, it's more like a hotel system, right? So guests are checking in and checking out. So these are the 3 methods which I will need to implement. One is check-in, one is check-out. Another is the API thing which I was talking, is get anagrammed name, right? So how do we do that? Let me just quickly check. Yeah, so I have that. So simple, right? So in this case, I have a guest cache offer, which is a hash map. correct? And what I have done for check-in, whatever name I get, I do a sort of it. So sorted name. And then what? I start with int count is equal to 1, correct? What I do look is look for my current cache if it contains the key sorted name. If it is already there, that means someone already is there with the anagram name. So what I will do is get the current count and update the current count by 1 again, right? Because new guest has come in. If I don't get it, my count remains as 1. So what I do, again, I update the key with the new count value, right? So this is how for check-in. Similarly, for checkout, what I do, again, I do a sorted name, correct? And let get the count. If count is equal to 1, what does that mean, right? So that means the with the same anagram name, the last person has checked out. So what I will do, I will remove from the guest cache that whole name itself. Else, what I will do, I will update it with a reduced count. So that's how I make sure my check-in and checkout are perfect. And anytime when I get and query to find the anagram name, what I will do again, sort it and just look up my cache and get the count, whatever is there. That's the number of people who are there with the anagram's name. And sorting is another method which I have written here. So let's just check this example, how this thing will work. So this is an example to use a hash map as a cache for this system. So what I have done, I have created a hotel object, checking in all the people, 6 people over there, and looking for anagrams. So right. So if you see ABC, BAC, CAB is there, right? So anagrams of the name ABC is 3. Anagrams of name CAB is also 3, right? Because it's the same word, ABC and CAB. And AAB is 2, correct? Then what I'm doing, I'm checking out BAA, and then anagrams of AAB is 1. That's how it's reduced now, right? Cool. So any you guys are clear with this, right? Any questions on this?
Instead of sorting, what if we use the ASCII values and add them up? Because ABC, BAC, and CAB will all give the same sum of ASCII values.
Will it always give the same?
If
When you talk in terms of values, right, it can be different also, right? Now think of, say, for argument's sake, ASCII value of A is 1, B is 2, correct?
Mhm.
So ASCII value of a single character B and a double character AA is also equal, right? 2, 2. Did you get my point?
No.
So for say argument, for argument's sake, A ASCII value is 1, okay? And the ASCII value of B is 2, correct? Now, what will be the ASCII value of this string A? Tell me. 2, right?
Right.
And what will be the ASCII value of just this string? This
2.
is also 2, right?
Right. Got your point.
So we cannot do that. So ASCII value is what other thing you can do is something like this. So if you see, that is something called as encoding, where you store, if it is AAB, right? You can store it like something like A2 B1, something like this. Got my point? So you do a encoding of it. Cool. So that's all I had from hash maps and hash set, which I missed last time. So let's, the next topic we will start would be on trees. So how many of you are aware of trees? Just quick show of hand. You have this reaction in the in your Zoom. So what is a tree? And also let me run the
It is a data structure where it can is stored in the data is stored in branches. Like it is stored in a hierarchical way.
Parent node and the leaves.
Okay, so let's go over now. So so we have discussed about arrays and all, right? So what's the good thing about arrays? So is it sorted or non-sorted?
Arrays are not sorted.
Okay, and what about linked list?
Linked list is also not sorted.
Interesting. And now what about trees?
Binary trees are not sorted, but binary search trees are sorted.
Correct. So yeah, so if you see, basically binary search tree is a data structure which has the benefit of linked list because it is also connected in the almost in the same way. Not a singly linked list, a doubly linked list. It is also having a left and right pointer, and it also maintains the property of order. So that's why trees is even more interesting data structure. Cool. So let me start.
Huh?
Two participants have raised hand. Is there someone have any questions till now? If you have, you guys can unmute and anytime feel free to ask the question. Cool. So yeah, arrays are unordered, right? Of course, you can do a sorting on top of it. So by default, it is unordered, but you can make an ordered array. Linked list also are unordered, right? Now what? Within tree, you have this advantages of an ordered array and a linked list. So searching is as fast as an ordered array, and what it also gives you the benefit of insertion and deletion that becomes fast in a tree. So that's the most important thing about a tree. So tree is more like, you can think of it's like a hierarchical way. So the example, if you see here, right, is an example where you divide things into categories. Like if you know about encyclopedia, right? So that's a big book which contains all of it used to be pre-Wikipedia age. There used to be book of Encyclopedia Britannica. So inside that, you can divide it into science and culture, right? And then in culture, you can divide it between art and craft, right? So this is how a hierarchical data structure looks like. So what would that mean? All of art and craft is part of culture. Culture is part of encyclopedia, but art and science, which are in different branches, they are not connected in any way. So yeah, so trees are connected by edges, right? So there are nodes and then there are edges, right? So the edges are the pointers or the connections which we make in the tree, right? Nodes contains the data part of it, right? So either you can have any complex objects over there, or for simplicity, if it is a binary search tree, right, you can even have integer, pure integer over there, right? So that's how it is, right? And so trees are usually unidirectional. So how a tree is represented? It is represented by its root node. Root node. The root node is the top one. So in this case, encyclopedia is a root node. So a tree, whenever you get a tree, what you will get is the reference to this encyclopedia. And if you have to go to art, you will have to follow this path. Go to encyclopedia to culture, culture to art, and then only go down. And from art, you can never go up. So usually trees are unidirectional. Right, so follow a path along the edges. That's what we are talking about. So yeah, what are some of the key terminologies used in trees, right? So first thing is path. So path is what I told, right? So it's like if you can reach from one node to another in one direction and reach there successfully, that means there is a path which exists from node A to node B. The root is the top of the tree. Whenever you say parent, right? So any node except the root has exactly one edge running upward, right? And the node which is above is called as parent. So for example, in here, right? The parent of science is encyclopedia and parent of culture is the encyclopedia. And only the root node will be there, which will have no parent. Child, similarly, the reverse thing goes for child, right? And a leaf node is a node which has no child. So in this case, all these nodes like science, art, and craft is a leaf node because it has no child. A subtree. So if you see here, right? So if you just consider this part of the tree, right? Culture, art, and craft. Itself, this is also a tree, a complete tree, I would say, who's connected with encyclopedia as the root, right? So this part of this tree, culture, art, and craft, is a sub-tree of the bigger tree with the root encyclopedia. That's the meaning of a sub-tree. Other terminologies is visiting. So visiting is a terminology used, right? So whenever you are traversing through a tree and you go to a node, that node is called as visited. And traversing, right? So traversing is a algorithm where you visit all the nodes of the tree. Levels is like, so level, when we say level starts with, let me see, yeah. So level starts with the root node is always at level 0. The next, all of his childs is called as at level 1. And level 2 is this one, and level 3 is the child of level 2. So for example, in this case, encyclopedia will be in level 0, science and culture is in level 1, and art and craft is at level 2. So that is the level of a tree. Key value. Yeah, so if you want to search something, that is usually called as a key. What you want to search in the tree. Now what? Every node in this, so what is a binary tree? So now if you think of a tree, in general, trees can have lot of branches and lot of childs, but That is not in our current scope. There are many trees, B tree, I think, and then there are other trees also, which is complex data structure. But for this session, in general, what we concentrate is binary trees. So binary tree means a tree which has exact two child. One is its left child and one is its right child. And and height of a tree is exactly is equal to your level plus 1, right? That will be your height of a tree. So and so this tree looks like a very complete tree, right? Where we have all the nodes, and all the nodes have two children of each other, right? And but think of this, right? Not all the trees will always have so many elements and it is completely there, right? So some trees can be unbalanced, right? So what is an unbalanced tree? Like that will mean, like, if we consider all the nodes of your left subtree and the right subtree, if they are equal for the root, that is a balanced tree. If they are not equal, that means it's an unbalanced tree, right? And similarly, all the individual subtrees also can be unbalanced. And usually, how does this thing becomes unbalanced? If it becomes unbalanced, if you are deleting some nodes or you are inserting in some order or some random order, right? That can also result in an unbalanced tree. So as someone mentioned initially, right? So binary trees, and the difference between a binary tree and a binary search tree is that binary search tree is a variant of a binary tree where it follows a very specific constraint that if the parent is there, so there are three things, right? Parent, left, and right. So for each nodes, the left will be smaller than parent and the right will be larger than the parent. And if this condition is satisfied for all the nodes of a binary tree, it is also called as a binary search tree. So now think of creation of a binary search tree where you are inserting a data which is already sorted. So in that case, how will it look like? So it will, all of them will go in one side, right? So that is an example where an unbalanced tree will be made. So that's what it is. This point is there. If the key values are inserted in ascending or descending order, tree will be unbalanced. So if you are, I think you got the point, right? If you are entering keys which are always greater, it will always go to your right. So it will basically a tree will look like a linked list, right? So where all of its nodes has just one right child. How do we insert? How do we represent a tree? It's represented similar to a linked list, but a doubly linked list, not a single linked list, right? Why? Because we have left and the right child, right? So usually it is stored as a, mostly it is always stored as a linked list, but sometimes you can also represent it in an array where there is a quite a very interesting way to implement in array that we will see. This is how you implement. This is a binary tree ADT, abstract data type, as we mentioned, right? So B tree will look like this. You for integer data, int data, and the left child, right child. What are the functions which you can do is find, insert, and delete over that, right? So this is how a tree will look in a using a doubly linked list. So yeah, this is also sometimes called as a full binary tree, where each non-leaf node has two children and all the leaves are at the same level. So this is the full binary tree, exact complete tree, right? So these are some of the examples of a full binary tree. Non-complete. Why? Because in case of binary tree, the insertion should always start from left node, right? So why the third tree? This tree is complete but not full. Why? Because you inserted something towards the left. So this is another example of full and complete. And this is also a complete tree, right? Why? Because everything on the left is exhausted, and then when you do it on the right. So these are not complete is not that important, and full is more important for any of these. Cool. So yeah, how do you store it in a array? So if you have to store it in an array, right, what you can do is you start the root node with the 0th element, and what will be your, so for any root, for any parents, its left child will be at its index 2 and plus 1. So 2 of 0 plus 1, which will be 1, right? So D is here. Similarly, the right child will be at 2 of your parent's index plus 2. That's how you represent it in an array. Left child of a tree is equal to tree will be there at 2 into your index plus 1, and 2 into index plus 2 will be for right. And very interestingly, if you see, all the leaf node will go from whatever is the number of elements, that half till -1, right? So if you see here, what are the leaf nodes? A, C, E are the leaf nodes, and then H and J are there here, right? So H, J, A, C, E, all of them are from 5th element till here, right? So number of elements are 10. So half of that, 5th to here, will be all the leaf nodes will be there. That is a representation, array-based representation. Yeah. If it is not a full or complete, you need to give some dummy nodes, right? Something like -1 over there, which will represent that this is a blank. So for example, 60 is at index 2. So its left subchild will be at index 5, right? So index 5 is -1, which means the left subchild of 60 is blank, null. Similarly, for 29, if you see, 29 is at index 3, right? So the left subchild of this will be at 7 and 8, right? So both of them are -1. That's how you represent nulls inside an array, in a array-based system. So what's the bigger problem you see using array and a linked list? What are some of the advantage and disadvantage you guys can see? Tell me. Hello. You guys can hear me, right?
Yes.
Yeah,
Cool.
the
So,
insertion will be complex in case of array.
why will it be complex?
Because when you need to insert the element, you need to move all the elements of the array. Will that take the time complexity higher?
Will you need to move all the array elements? Because if you see, where will you insert? You will perhaps insert at this position, which is already -1. You can directly go and overwrite here, right?
Yeah.
Inserted in between, you don't need to move anywhere, right? And if there is a leaf, after that, anyway, things are blank, right?
Yeah. Yeah.
Insertion can be a problem if your size of array is fixed, correct?
Yeah.
In that case, if you want to insert, you will need to copy all the elements in the exact same position in a bigger array and then do an insertion.
Yeah.
Yeah, so that's a valid argument now. But in case of linked list base, since all of them are independent, you don't have to define previously the size of it. You can insert at any time, because all you can insert till your RAM is there, right?
Yeah.
What more? The biggest problem what you see here. What is the bigger problem here? So one thing is instruction, what is another? This, right, dummy nodes are required for trees, which means if a tree is balanced, it's fine. But if it is not balanced, you are using so much of space, right? For storing of -1, that dummy value also memory is getting wasted, right? So all these dummy values, they require to some space. So that's a very big problem, right? In array-based representation. Cool. Yeah. So this is shown in the same way. So yeah. So now array-based representation for binary tree and binary search tree that's why never used. You will see this array-based implementation. Why I wanted to touch was because this will get used in heaps. So now let's go into the different operations which you can do on a tree. So binary tree are always represented by the linked list, and in terms of traversing the tree, there are three ways you can do a traversal: in order, pre-order, and post-order. So what is the meaning of them is so first thing first, whenever how do I remember that? So lot of confusion always occur with everyone. Well, how do you remember what is in order, pre-order, and post-order? So let's take this example in here, right? So how will it? So every time in order means everything is with reference to your root node. So now if you see in visually, where is the root node? It looks in between left and right, correct? So what will a in order traversal mean is that first print your left, then your root, and then your right. Say there are just 3 nodes. That's how it will. So if there was just a tree of this tree called GDI, so the in order traversal will look like D as in Delhi, G as in Gurgaon, I as in Imphal. So that's how the in order traversal will look like. What will pre-order traversal look like? So pre means previous, right? So G will come first. So G and then left and right. So always left and right is always in between them, left comes first, right? That's how we even measured the completeness. So pre-order traversal of 3 nodes will look like G, D, I. Similarly, post-order traversal, how will it look like? Post means it comes after. So G will come after left and right. So left and right are always together, right? So DIG, that will become post-order traversal. So these are the 3 ways using which you can traverse a tree. And what's the benefit of these things? You will see in later. Why do we even need 3 ways to travel, right? So now if you think of this as a bigger way, right? So we just did it for 3 nodes. Now if you think more about this whole node as a full, right? When I talk about pre-order traversal, which means not just the current node, you need to look at all the value, all its left and right subtree also. So what does that pre-order traversal of this will mean? Like, okay, for G, you will print the left. So it comes to D. Now what? If you see D itself is a root, it's a parent, right? So you will need to apply the same logic for D also. So you cannot print D. You will need to print B first, right? But then when you come to B, you see that B itself is a parent. So you cannot print B still, right? So what you will go, and you will go down to A. You see A, it is a leaf node. It is no more parent is there. So first, what will be printed will be A. And then what? In terms of pre-order, it sees, it prints B. And then what? Tell me, what is the next node which will get printed in a pre-order traversal? So similarly, now the right of this B will get printed first. Then only it will come back to D. So A, B, C, and then D, and then it comes to F, right? F is a what? Itself is the parent. So you need to first print the left subtree of this F. So what? It will come to E here, right? And then F, and then G. Then it goes to I. I itself is a parent. So what? It goes to H, and then it comes back to I, and then J. So the pre-ordered traversal of this tree will be A, B, C, D, E, F, G, H, G, H, I, J, which is exact alphabetical order. Correct? Can you guys now tell me what should be the sorry, this is I'm really sorry. This is all what I said was in order. And what should be the pre-order traversal of this tree? Ping me in chat. What will be the pre-order traversal of this tree? So in order traversal A, B, C, D, E, F, G, H, I, J. What will be the pre-order? Anyone who can volunteer, or if you already are typing, can you ping on chat? Manisha, G, D, A, B, A. Cool. So Manisha, you want to walk us through how will it work? Just unmute yourself and then go ahead. And by
hello.
Yeah, go ahead, Manisha.
Yeah. Okay, so since it is pre-order, we'll print the node first, then left and the right.
Yeah.
So we'll start with the root node. So it will print G first. Then it will go to the left node. D is again the root of that left node. It will go to D. Then again to the left we go. Then it will go to B. Then it will will print the B first. Then A, like that will go. So we have reached the leaf node. So it will go to the right side now. So it will go to C. Then again it will go back, and since it has already printed D, it will go to the right now. So it will print F, then E, and then again we'll go back, then we'll go to G. Since G is already printed and left is printed, we'll go to right side now. So right side we have I, then it will print I, then it will go to the left side, which is H, and then again, since it is leaf, it will go back now, and it will print, yeah,
J.
right, J, yeah.
Correct. So that is this is the pre-order. Similarly, can you guys work on the post order? I think yeah. So I think everyone got the idea. So in the interest of time, let's move ahead. Devajit, sorry, I was not. I think you were speaking something. I couldn't hear you. You can go ahead if you want to go through. If you have already done it, there was someone who was speaking something, right? Yeah. So yeah. The post order, everyone, lot of people have printed that A. Yeah, so you start with G. What you see is you go towards the in post order root will be printed last, right? And first left will be printed, then the right, and then root. So you go all the way down to A, which is left, then it's right, which is C, and then B, right? And similarly, uh, you go back to from B, you have to print F and then D, right? So that's how you will go ahead. Cool. So let's move ahead. How would the algorithm look? So in terms of recursive, it's simple, very, very simple, right? So in order, how would it look, right? So what you have to check, if it is not null, right? Call in order of its left subchild, print the data, and call in order of its right subchild. As simple as that. And similarly, you can do a recursive for how would can someone tell me how would a algorithm for pre-order look like? If this is the exact same algorithm, if you have to mention in recursively.
We'll first print the.
Yeah.
Yeah, go ahead. Anyway.
So we'll first print. So we'll first print the root and then call pre-order left child, then pre-order right child.
Pre-order left child. Yeah, correct. So that's how. So the algorithm is almost the same, and then yeah. Just the way you print and call the methods, that will change for all of these three, and you will get different outputs. And very interestingly, so if you have seen, so the traversal can be done in any tree. BST, BST is binary search tree, BST or a binary tree, any tree. But if you do it on a binary search tree, BST, the output of a in order traversal is always a sorted one. So all you get a sorted uh, output for BST. Yeah, so it's the same thing, pre-order within the node call itself, and then post order it is. And then these things are also used to generate the infix and the postfix expression of a equation. Cool. And now what if you have to think of this BST? BST is what? A sorted array, right? So how do you do a search in that, right? So given a key, how will you look for a key? So that also, if you see, is simple, right? So uh, say if you have to, let's get back to here, which is already basically, if you see, this is a BST in terms of string, right? So say if we have to find the element f, right? So how do you do? Go ahead and do. So you start with the root and you check, you compare it with the root value. Is it equal? No, it is not equal, right? So what is f? F is smaller than g, right? So what? Now what you need to do? You call recursively the same method and give the left child of g to be searched. So what? You go to d now. You compare with d. Is it equal? No, it is not equal. But f is greater than d, right? So now what you do? You give the right child of right subtree, I would say, right subtree to do the search from. So what? Now it comes to f. It is equal. Yes, it is equal. That means you have found f. So how many operations do you think this required? How many comparisons did we did? We did just 3 comparisons, 1, 2, 3 here, right? Correct. Before we found out the array, right? So we found out the number, right? So the time complexity, since it is divided into half sort of, right? So the time complexity is log n. So search time complexity is log n, given that if there are n nodes inside the tree. So, and why you get this log? Because if you see, right, the whole n nodes is divided into different levels, right? And there is an equation which you can find. If given a number of levels, if it is L, you can find total number of n nodes also, right, in a complete binary tree. It will be, I think, 2 to the power n minus 1, something like that. So that's why you get this logarithmic time complexity here. There is a math behind it, which you guys can look up. But for the sake of time, we'll just skip that. Now, coming to the insertion, right? So insertion in a BST, if you see, that's what we are doing, right? So BST, right? So first thing you need to find out is where you want to insert. Since the data is already sorted, right? You will need to make sure that the insertion happens at a correct place, right? So that's what it is. The first line is that to insert a node, you must find the right place to insert it. So for that, you will need to find a correct place. What it means is it will mean like since it is sorted, the correct position, right? So you start from the top, follow the path from the root to the appropriate node where which will be the parent of the new node. So you have to find like, okay, which where do you want to insert and what is the parent, right? So when this parent is found, the new node is connected to its left child or the right child, depending upon whether the new node's key is less or greater than of the parent, right? So that's as simple as that, right? But in this case also, there is a big problem. What's the problem here? Can someone tell me? The problem, there is a problem, right, in all of this thing. Okay, so I'll come to that, right? So in this insertion, also the time complexity will be log n only, right? Because what you have to do is finally find the level of it, correct? So in terms of, let's quickly see how does all of this thing looks like in terms of a code. Do I have that? Insert. Yeah, so this is how the recursive insert looks like. So this is a binary tree, right? So node left, node right, and node data, sorry, int data. That's the node class for me for a binary tree, correct? And you start with root is equal to null always, right? And whenever you have to insert, what you do is you will get a new data which you need to insert, right? So for that, I have written a helper method where I take the root node and then insert it with the correct data, right? So if the root was already null, what I need to do is just create a new node with the data, right? So whatever the data you get, that becomes your node, right? And that is returned as the root node. That becomes your root node. Else, what you have to see, if data, if data is less than equal to your node dot data, node is your the root we are getting. So if that is less, that means you have to insert it in your left part of your tree, correct? So that's what is I am doing now, right? What I am calling is telling that do the insertion where my root is node dot left with the data, and what will this insert return to me is the root of the new inserted uh, subtree, correct? And that's what I connect it with my current node's left child. Or else what I do, similar thing for my right part of it, right? So exact similar thing is done in right. So what would it mean in terms, if you see here in my PPT, say I have to insert a new node called as Z. Is this a BST? Yes, this is a BST, right? Right, right. So say you have to insert something called as 60, uh, uh, something like 50. Oh, sorry, 50 is already there. So say you have to enter something like 55, right? So what will happen, right? You start with, you give the node 50 to, you start with here, you check 55 with node 50. Is it bigger? Yes, it is bigger. That means you need to insert into the right subtree. So you give the subtree with the node 60 to it. What it will look is is 55 bigger? No, it is not. So what you have to insert in your left subtree. So what you call this thing with null, right? So you call your left subtree, which is null, and you give the data over there, right? So in null, what it was doing, it was creating up a new node, right? So a new node 55 will be created, and the reference of that will be given to 60, and 60 will connect it to its left subchild. That's what exactly is happening here. So that's what I meant with the code here, right? So that's why we are connecting it. So when it will come to 60, what it will see, it is data is less than node dot data. Yes, it is. So it will call what? Insert node dot left. Node dot left of 60 was null, right? So it comes back here. Node is equal to null. Yes, it is null. Then what? It creates a new node and returns the reference of node, right? Which I am getting as a return of this insert statement, and I am connecting it with my left. So that's how whole insert works. Any questions do we have till now? Cool. So insert is simple. Finding insert is there. Finding min, right? So in a BST, finding minimum is very simple since this is a sorted ordered tree, right? So the minimal value will be the leftmost item, right? So keep on going to the left until you find a leaf node. So that will be your minimum item, right? And exactly for maximum, you do the same thing. You go till you find a right? So for example, in here, if I have to find the minimum, I will come from 50. Does it have a left? Yes, it is 40. Does it have a left? Yes, it is 29. So 29 will be the smallest item in my subtree. Similarly, if I have to find the maximum, I will start with 50. Does it have a right? Yes, 60. 60. Does it have a right? Yes, 70. 70 is the maximum item. So that's how you find the minimum and the maximum in a BST. Deleting a node. Okay, so I'll quickly go over a deletion. So deletion is a bit complex. So we'll quickly go over deletion and then end this session, right? So so there are three conditions where you want to delete, right? The node itself to be deleted is a leaf node. Other condition is the node which has to be deleted has one child. And then the final condition and the most complex condition is that the node which has deleted, that has two children. So what will you do, right? So let's take this example, right? For this example, we have to delete 20, right? So that is a leaf, correct? So very simple. Just go ahead and delete this thing. Deleting it, what it will mean is like you make the left pointer of 30 as null, right? 20 will automatically get deleted. Node that has to be deleted has one child. Say you have to delete 30 in now, right? That is also very simple. What you do is you delete the 30th node, and what you do, you connect your previous node, you bring this as parent, you make this as parent. So what will that mean? The parent of 30 will become will be connected to the child of 30. That's simple, right? Deletion of 30. But the deletion when you have to do with which has two children, delete in case of now if you have to delete 50, that is a bigger problem, right? Why? Because you have to now make sure you bring in the correct item on the top, correct? So what you in case of if you have to delete a 50 here, so in this tree you see what is the number which can come in terms of in place of 50. Can someone tell me? So in any array, right? So at 50 is a root here, right? So at any position in a binary search tree, where is the next element of your current element? I'll quickly run the polling. So the element which is eligible will be the of course what we do take care in that we look into the right subtree of this array. So the right subtree is this part, right? 70, 60 and 80. And within there we find the smallest number. So what will be the smallest number of right subtree? The leftmost item of your right subtree. So this is 60. So what you do, you make 60 as your you bring 60 instead of that current node which has to be deleted. So that's the deletion algorithm. Let's quickly look what more is there, right? So Deletion of leaf node we have connected. Deletion of one child also is connected, is covered. Deletion of two child, right? Okay. So now, for example, so delete a node with two children. Replace the node with its in order successor. In order successor is also something like what you do is to find a successor. Start with the original deleted right child, then go to its node's left child and to its left child, and so on, following down the path of the left child children, right? So the most minimum, the last left child in its path is the successor of the original node. That's called as the successor. And that becomes the successor of the deleted item. So I think I'm running over time. I quickly have another meeting. So I will stop here. We'll continue with deletion in next session because I think we need to get a more dig deeper into this deletion because it's a bit complex. So quickly, do we have any questions till now, except deletion? You guys are, I'm still audible, right?
Yes, sir. So yeah, all good.
Cool then. Okay. So let's quickly end this session. I'm already 4 minutes late to our meeting. I'll continue with deletion in the next session.